Okay, we're now moving to our second, I will get the label correct. Yeah, so we're now moving on to our third talk. And our third talk is by a speaker joining us from Bangkok in Thailand, and his name is Poom. So I'll bring Poom onto the stream and get the labels. Hey, Poom, nice to
Hello,
meet you.
can you hear me? Nice to meet
Yes,
you.
welcome. So you're joining us from Bangkok in
Yes,
Thailand.
yes, exactly. I'm joining from Thailand.
Great. And so I want to give a little introduction. So Poom is a developer advocate at BRIKL based in Bangkok, Thailand, and he enjoys building silly apps with React. He tinkers with cutting edge stuff like Rust and WebAssembly and customizes his dot files for fun. On other days, he runs community projects like the Stupid Hackathon Thailand and the Young Creators Camp to get Thai developers to keep hacking. Or he's just relaxing at an onsen bath in some corners of Bangkok. So it's nice to hear that there's onsens in Bangkok, but that's not today's
Yes,
topic. So today's topic for your talk is going to be why you might not need advanced types. Is that right?
yes, yes,
Cool. So without any further delay, you ready to share your screen?
yes. Let's do it.
Let's do it.
All right, can you see my screen?
Yes, we can see your screen.
Yes.
We're getting a nice effect here. Great.
Okay, does it work?
Yep, you're live and it's all good to go.
Okay, thank you. So I will start now. Okay, everyone. Nice to meet all of you. My name is Poom, Phoomparin Mano, and I'll be talking about why you might not need advanced types today. Okay, so my name is Poom, and I'm a developer advocate at BRIKL from Bangkok, Thailand. And it's true, yeah, I like to enjoy onsen bath in Thailand. But most of all, I organize a lot of like developer community projects for like students and university students in Thailand, like Young Careers Camp for people to make their own products, and the Stupid Hackathon Thailand to encourage Thai people to like build stupid things. Yeah, and you can follow me on GitHub at Phoomparin. So let's begin now. Okay, so the story of this talk is I see a lot of developers. Most of them like they have a good grasp on TypeScript, but most of them haven't even checked out the advanced type section of TypeScript. And I'm one of those developers too. And I believe in a saying that learning in public is like really helpful when you're learning new technologies. So I'm pretty new to TypeScript to myself. And that's why I have a question. When do I need to use advanced types? So this has been a question that's running on my mind for quite some time. I don't know like when the need for conditional types or like using the advanced features will come up. So today's talk is mostly for people who haven't touched that section. So if you have already, this is like a good opportunity to like refresh the knowledge. Okay, so in my scenario, the scenario I see which is perfect for learning about advanced types is building a schema builder. Like as the last talk, like as Ethan already said, when you're having like a very dynamic object like a JSON, it can be very hard to validate or very hard to like get them to be type safe. So I think building a schema builder is going to help me learn on this. Okay, so since I'm a hackathon organizer, let's make an app for grouping people in hackathons. Yay! Yeah, so I'm the organizer of the Stupid Hackathon Thailand, and one problem we have is people in hackathons usually they don't know like who to group with, who be the perfect team to like the hackathons with. So let's make like an app for them. But first, let's look at the API surface. Let's look at the API that we are gonna be making a schema. So when we are organizing a hackathon, there's gonna be people joining us, right? So they're going to be a member. So this is what my API for our query builder might look like. I might have like a type function that constructs a new type, and then you can use a function like ID, text, and number in order to construct the fields. And this looks simple enough, right? Since this is just scalar types. But it can get more complicated. Like in a hackathon, you might have a team, and in that team, you might have a team lead, which is a reference to a member, or you may have the list of members, which is an array of a reference to members. And this is where it gets interesting. So when you're building like something like this in TypeScript, I think pretty much the challenge here is this. So not only you have to construct like a query builder in order to construct like a JSON structure, but you also have to create a type in order for the resolver to use as well. So this is the challenge for today. Okay, so how would we write this query builder just for the types? Like we don't care about the correctness, we just need the types to be correct. And this is how I would do it. So looking at this structure, you can see this is just a pure function, like a function to construct a type, an ID, a text, a number, which is like the scalar types and the type. So I would do something like this. So I would make like a text that returns an empty string, or maybe like the number function that returns an integer. So this would give us the correct type. And if you look at this, well, it looks pretty legit. We got a type of name, which is a string, and a type of age, which is a number. So it looks already good, right? Yeah, and even for arrays of references, that's already looking quite well. So what's the problem here? The problem here actually is, well, actually when you look at the create handler function, the types here is going to be working. So it looks like it's going to be easy. But the fact is, we are not done here. Yeah, we're not done because we're just constructing the types. But in order for an app to be functional, not only the type has to work, but we has to have the JSON structure for the schema. For example, it might look, well, I will show you later. But for now, let's just use like a plain JavaScript object and pure functions to construct the structure. So this would be how I would do it. So I would have like a function of type, and that would return the type of schema, a function text, and that would return the type of string, a number, and that would return the object with type of number. So while this can provide us with the structure, for example, if we construct it like this, if we compose it like this, with type of project and with text and with reference to team and so on, we would get a JSON structure that looks like this. And while this might look legit, like if we look here, well, we got the name and the type of string, we got the type of ref. So the schema here actually looks good. But the problem here is, then we are failing our second requirements. Because if you look at the types here, then everything is now any, and this is certainly not fine. So even though our JSON structure is correct, our type is completely wrong. So how would we fix this? So what we need to do is we need to not only generate the type in the code, but also in the Typeline. And this is what I mean. So if you create a function like this, if text returns the type of string, then the problem is that string constant is not going to be there because the type is going to be widened to string. And it's going to cause problems because then you cannot figure out if the type is a number or if it's a string. And this is a problem. But this is easily solvable. So you can just put type is a string. And then TypeScript knows not to widen that type. And it's precisely string. So this is the foundation that we will be building on. So the mission here is we will need to preserve the information in our types in order for TypeScript to be able to parse that type structure. So we are already doing a good job here. We are already putting the type, like for strings, numbers, arrays, references, and optionals. So now the structure has a correct type. And it is easy to go from here because even the schema and the name is preserved at the type level. so the information is not lost. So everything still works great, right? And if we look at the type, so if we hover over to the project constant, we can see that the type, the name, the schema is all there. So we got enough information for the TypeScript compiler to work with, which is very nice. Now, if we look at another example, so this is the schema of the team in the hackathon. You can see it has the type of string, and the team lead has the type of reference. Okay, now back to our problem at hand. The goal here is to be able to create a resolver function that gets the type that we created, and it allows us to populate it. But remember, we are not creating this type by hand. We're not creating the interface of the type, but we are auto-generating it from the constants. So how does that work? And that's our next task, actually. So we have to generate the return type from our structure. So if you remember our structure, it has a type, and then the string of what the type should be. Should it be a number, or should it be a string, or should it be an array? So let's begin from our scalar types. So the goal here is to map the type to number and type string to an actual scalar type in TypeScript. So you can do this pretty easily by creating an interface with a mapping, and you can do a type scalar and key off in order to construct a union. So now we have a union to work with, which is pretty nice. So now we just want the type field. We want to access the type in the schema. So ideally, we should be able to do something like this. So we should be able to get the schema, and then we access the type on it. So this is very similar to a function that Lodash has called map values. So it just maps the values to the type, which is pretty straightforward. So now if you look at the result, now we are getting very close. Now we're getting name of the string of string and the age of string of number. So from a structure, now we got rid of the types field and map it directly. Oh, but then again, if we were to map the type mapping to the native type, we're gonna get a problem. And why is that a problem? How did that happen? So the reason that did happen is because the TypeScript compiler didn't have enough information. So it cannot ensure that the type key is a scalar type at all. It doesn't know for sure that's a scalar. So how do we do that? And the answer here is to use conditional types. So what is a conditional type? So a conditional type, you can check if the type extends another type. For example, I can check if a type extends a scalar, for example, a string of type string and an object of type shuttlehoo. So you probably know what this results in. Yeah, so a string is a scalar, so that's a yes. But the type shuttlehoo is not a scalar, so that's a no. If that becomes yes, then you have a serious problem more than TypeScript. Okay, so now we got this scalar type mapping, and now we can apply it to our type field, which the type field is just a string of number or a string of string or string of array. So now we're going to get a concrete type. Great. Okay, so how about references? How do we build a reference? So let's look at our API surface first. So we use auth to construct a reference object to another type. So this is what it looks like. So you can see the type in TypeScript. It says that type is a ref, and an item, it has the structure of the reference type. So person has a type of person and the schema. And the problem now is, how do we get the item generic inside a reference? Since if we can get the item generic that's nested here, we can get access to the schema, and we can map over the schema to make it to become a concrete type. And that will solve our problems, right? So how do we do that? Luckily, with conditional types, there's another keyword called infer. So a nice thing about infer is it allows us to infer the type that is contained inside the generic. For example, if our type of ref here, we have like a nested schema, which is like from another type, we can extract that. So if we try that out to get the reference item using this given structure, then we can see that, hey, we successfully got the ID and the string. And that's pretty nice. So we can just map that. Okay, now let's put all of them together in one package. Ready? Here we go. Yeah, so this is looking like pretty Halloween-ish. This is looking a bit scary. So to most people who haven't done like TypeScript heavy before, this can look like pretty intimidating. But because like we have been here for a while, then we know that this is a conditional type. And we know that this is mapping to a scalar, which is using the type field. And we know that the ref here is just extracting the schema from inside the nested object and map that back recursively so it gets mapped into a scalar type. So that's not too bad, but we can refactor it and make it a lot better by sprinkling some comments. And let's do that. So if we sprinkling some comments in, we can see here it's a lot easier to read. So we know for sure, oh, is it a scalar type? If it is, then we just map it. If it's a constructed type with t.type, then we just recursively map it. Map it to a schema. Okay, and that's looking great. So now let's add in support for arrays. So what is an array? So in a hackathon, we may have many team members, and our query builders, a schema builder is looking like this. So we have many of member. So many is like constructing the array objects, and of is constructing a ref. And now an array can contain both a reference to another type and a scalar. So now we can just apply it recursively. For example, now we have the item, which is extracted from the array objects. So now we can see that there's an item. We can map that recursively, so it can become either a scalar or a ref, and then be mapped into a native type. So that solves our problems, and we can see it here. So if we created a structure that looks like this in the type world, type of array, which contains a reference, which contains like a schema. So when we map that recursively, we will just get like a concrete type, like a native TypeScript type, which we can use to annotate our projects. Okay, so this is how the generic map box input to return type would look like. So if we get an input, this generic can either accept an array or a reference. So first it checks if it's an array. If it is, then it maps and make it an array. Otherwise, it checks if it's a ref, and it just extracts the schema inside of it and map it again. Otherwise, yeah, just map it. Yes, so what it does is to unbox the values in the type. And if this is your first time reading a code that looks like this, I know it can be pretty difficult to wrap your head around because like of the recursive nature and like how you usually program in code, but now you're doing it in types. And finally, we can apply this to every field inside of the schema structure. So let's take a step back and let's look at what we did. So we have this function that maps an array and a reference. And then we have generic. And then we have another generic, which maps the scalar type and the constructed type into a concrete type. So if we do this, and then we map it for everything in the schema, then sure enough, we are going to get a working type. So now we can see that from the type in the schema builder, we can use type of to get the schema inside of that type. And then we can just do this. We can just use that type and it will work perfectly, which is nice. And there goes our both requirements. So the first requirement is for the schema to be typed as a JSON structure. And we can solve that pretty easily by constructing an object. And second is by building the TypeScript type to use in our resolver. And that can be done pretty easily by using conditional types and recursively map types. Okay, and yeah, that's what we did. So we did it. And let's do some more practice. So we now have scalars, types, references, and arrays. So now let's create an enum in our schema builder. So this is the API that you would expect an enum to have, right? So it would like get the list of options, and then it would allow the user to just pick one. So that would be a union. But the question is how do we turn a string array into a union? That's pretty hard to do. So I know the easy way to go about this is you can use ascons. So that will turn it into like a read-only array. And then you can use type of notation here of number to turn it into a union. But there goes the problem. I don't want to use ascons in the user code. So what can we do about this? Luckily, there's another way. So you can use this. So you can use like a res operator to kind of construct the choice into an array, and then you make that a generic which extends a string, which is precisely what we want. And this will allow us to preserve the string type. So that will not widen the type to be like an array of string, but that would preserve like the choices in our enum. So that's great. I think now the logical thing to do about this is we can just extract the choice from this generic, right? Well, not so easily. We can see a problem here, which is when we do choices and index that by number to turn it into a union, we found another problem. So if you remember back to the beginning of the talk, this is precisely the same problem. So TypeScript doesn't have enough information to ensure that it is what we want. So it doesn't know that choices is actually like a list of read-only strings. So we can hint our compiler a bit. So we can hint in the enum type, we can hint that, oh, this actually extends a string array. So this would be able to be indexed by number, and therefore it would become a union. So this is precisely what I did. And now we can use our enums as a union type. And this is pretty nice because you can just feed it like the choice like we did with the enum function, and we would just get a union out of it. So we get an auto-completion for all possible enum values without having to use ascons, which is nice. And now we're running out of time, so it's time for the final boss. So our final boss today is called optionals. So you might think, optionals? How hard can that be? Isn't that just like making like a field like not required? Okay, so let's try it out. So this is the API we want. We want our schema for the hackathon. Every team should be able to have their tagline, but not every team has to have a tagline, right? So we would use like a box type like optional. So we would wrap the structure with optional, and that would give us the information later that we can know, oh, okay, we don't have to make that required. So what could possibly go wrong, right? Can we do this? Like we make a generic that unions it with null and undefined. So maybe that becomes like an optional, right? Well, not so fast. As it turns out, this doesn't really do anything. So both name and age is still there. It's still required and not optional. So it's not very effective. And this is why I say this is a final boss, because it's pretty difficult to deal with. So let's take a step back and look at our type. So we have a type of name which is required, and that's going to be a string. But both tagline and age is optional. So that means it shouldn't be required to include into our object. And this is just a little bonus I found. So I found that by using the new type pattern, which looks like this, you can actually create a new type in which like the value itself will still be the scalar. For example, this hello string would still have the values of the string, the properties of the string, but it's going to be interpreted as a new type. So you can use conditional types to check for that. Yeah, but that didn't really help in this case, right? So I kept on searching and I found this on Stack Overflow. So I found this nullable partial generic. And what it does is, given a list of keys, it makes them optional. So I guess the magic here is null extends T of K. I guess that's the part that handles it, but I'm not really sure. So let's get our final boss game plan ready. So here's my game plan. So first we will create a type of optional. Then we will unbox that optional. But if it's not an optional, then we default to never. And then we get the list of the optional keys. And then we use nullable partial so that we will use the list of keys to make those optional. And then we can join the optional section and non-optional section back. So I know this sounds like pretty confusing. So let's see it in action. So step 1, create our optional type. We already did that. So moving on to step 2, we can unbox the optional type. So I'm using a generic here, which basically just extract it using Infern, and now we're getting a plain item. And by doing this, we can see that every field that's marked as optional now can be unboxed, and it's now just become like a type of string. But every type that's not optional just becomes never, and it makes it easy to check for that later. Okay, step 3. Now it's time to check for an optional keys. So now by using this filter keys generic, what we can do is we can filter out those. For example, a tagline and age exists and it's not never, so we know that it's an optional. So we can use this filter key generic to just get a union of what should be optional, so we can pass it to nullable partial. And that's exactly what to do next. So I can use this nullable partial generic, and then I use those two values, which is the optional fields and the optional keys. And then I pass that to nullable partial. And now we can see that they got like the question mark, which means now they're optional. And I know this is like pretty overcomplicated, and there's definitely a better way to do this, but this is more like a practice to like deal with a lot of generic types. And finally, we can just join the optional and the non-optional types. And now we can see we get what we want. Now only the name is required, and the age and the tagline is now optional, which is precisely what we want. Also, the extract and the exclude type is my most favorite. Since those, so basically what they do is they allows you to like exclude like a partial, maybe exclude a partial, not partial, I mean a particular union member from the list of unions. So that like really helps a lot. And we're almost done here, yay. And finally, about the talk title. So you can see like what I have spoken like now has to do with advanced types. So what does the talk title mean? So this is what I mean. You might not really need advanced types if you can simplify your API surface. And so what I mean by this is the first time like I did this like schema builder, I did it with classes first. And by doing it with classes, I ran into like a lot of difficulties, like having to use newtype. So the complexity of your type kind of depends on like how you design your API. So my recommendation is like to type your API first and then like implement it later. Because most people that is like a newcomer to TypeScript, they usually just like write the code first and then try to type it later. And that's not going to scale. And yeah, so maybe like a train of thought, maybe it might be even better if the end user just wrote their own types. Maybe that will get rid of the complexity. And it really depends. So I'm going to end with a closing note. And thank you everyone for listening. And if you have like any questions, please feel free to ask me, and I will post like the code to GitHub so you can try it in your playground. Thank you.
Poom, thank you so much for that. That was really it's always great to see like more and more talks going into deeper topics with TypeScript, but also it seems like one of the common problems that continuously comes back is this relationship between validation, runtime validation,
Yep.
and the type system, build time, type safety essentially. And so this solution that you came up with was essentially an API that allows you to generate both JSON schema, which you can use for runtime validation, and generate types using the generic, basically the type system to generate these types that you can use. And that was really cool to see. So thank you for that.
Thank you. Oh, sorry, I forgot to mention one thing. Yeah,
Sure.
so one more thing. Yeah, so BRIKL is actually hiring, and we're looking for like software engineers, like both in back end and in front end. And like the problems I show you today was actually like from one of my production work. So if you like to deal with this like TypeScript advanced types, then feel free to join us. That's it. Thank you.